Okay, so continuing on to 14.8, the Lagrange multiplier lesson, day 1, we're going to take a look at a second example. We've got find the points on this sphere, x squared plus y squared plus z squared equals 4, that are closest to and farthest from the point 3, 1, -1. Now, immediately I hope we can notice that our function g is our constraint. We're looking for points that are going to hold true to g equaling 4. And what we're trying to optimize, what we're trying to find the largest and smallest function value for is the distance formula. The distance formula in 3 dimensions is x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And what we're seeing is we've just got some arbitrary point on the sphere. We don't know what that is exactly, but we could call that point x, y, z. So our distance is going to be the square root of x minus 3 quantity squared plus y minus 1 quantity squared plus z plus 1 quantity squared. And even though we are optimizing a little d here, we could say that d squared, which would equal capital D, that would be so much easier to work with and to optimize that. So as we said earlier in this chapter, if we are going to maximize or minimize this distance function, that would correspond to also maximizing or minimizing the square of the distance function. So I'm going to call this function f that we have right here, and we're going to use some Lagrange multipliers. You know, what's just so nice in this regard is that we don't have to go down to 2 variables. Very, very quickly we can take a look at the gradient of f. Gradient of f would be 2 times x minus 3. This would become 2 times y minus 1. And this is 2 times z plus 1. And taking a look at the gradient of g. Well, the gradient of g, 2x, 2y, 2z. Of course, taking our derivative with respect to x, to y, and to z in those respective components. Well, what we're doing for a Lagrange multiplier is we are solving where the gradient of f would equal lambda times the gradient of g, but we'll get, in this regard, 3 separate equations with the x component, y component, and z component. But that's not the only thing that we're going to deal with in this system. We're also going to have our constraint. So this is super important, that while we are looking at the gradient of f being equal to lambda times the gradient of g, we can't forget that we also have x squared plus y squared plus z squared equals 4. So look, all we can do super fast here, making this problem easier, is to say, well, look at our I components. We're saying that 2 times x minus 3 would equal lambda times 2x. We'd also say 2 times y minus 1 would equal lambda times 2y. And then for our z component, of course, we have 2 times z plus 1 equals lambda times 2z. But as I keep saying, don't forget this all-important constraint. We're going to use that as part of our system. So really, our system is enclosed right in here. That's what we're working with. Well, of course, we can divide out a 2 for all of these equations. That makes life considerably easier. But let's just take a look at what we have for our very first situation here. We have x minus 3 is equal to lambda times x. How about I subtract lambda x and simultaneously add a 3. How about we also erase that? And I'm going to factor out an x. We'd have 1 minus lambda over here. And, as we're looking through this, we really have a choice on whether we'd like to solve for x or solve for lambda. And we really could go in either direction. And we could definitely do something rather clever right here. We could essentially just solve for our lambda, and we could have solved for lambda even earlier, to be honest with you. I think this is what the author does, and it's worth speaking of. He would solve for x with respect to lambda. He would do similar work with y and z, solving for lambda, and then he would substitute all of these x, y, and z expressions back in to our green highlighted constraint equation. And that's fine. It's something that you can see on our book, page, I think it was 985. It's rather messy, to be honest with you, but it's certainly something that you could do. I guess what I'd like to point out instead is that when we have this other option of x minus 3 is equal to lambda x, we could have very easily solved for lambda. Of course, we could still solve for lambda as we had an above equation, but the danger is dividing by x. And that's something that you don't want to do unless you know that x is not going to be 0. I do want to be very emphatic that you have to pay attention to that. But think about it. If x was equal to 0, this original equation just wouldn't be true. Lambda times 0 would equal -3, and that just isn't going to happen. So because we can, in fact, get a little bit of extra assistance here, we could say that lambda is just x minus 3 all over x. That being said, we can use that to substitute lambda into our other equations. Look, y minus 1 is equal to lambda times y, but imagine that our lambda now is thought of as x minus 3 all over x. Similarly, over here, we could say z plus 1 would equal, well, here's my lambda. I'm going to type in x minus 3 all over x times a z. And this is all well and good. That's fine. But what I'd really like to point out to you is that right now, for both of these new equations, I'm going to multiply the left side and the right side by that common denominator of x. And the reason why I'm doing it is to eliminate it. And what are we left with? xy minus x would equal xy minus 3y. All of a sudden, you can see the xy's cancel out. Look at that. That's delightful. That's wonderful. And then y would equal, solving here, x all over 3. Similarly, coming over to this other equation in regards to z's, how about I multiply the left and the right side by x once again? And the whole purpose for doing that is so that we could cancel out these denominators. We'd be left with xz plus x. Over here we'd have xz minus 3z. And the xz's cancel out. Z would equal, fantastically, opposite x all over 3. Very nice to have that. Well, now what? Well, we've got x squared plus y squared plus z squared equals 4. And my goodness, we could say that our y is x over 3. Our z was opposite x all over 3. Let's just clean that all up super fast. We'd have x squared plus x squared over 9 plus x squared over 9 equals 4. And this is 9 ninths plus 1. So I guess we'd get 11 x squared over 9 if we just combined like terms. So let me just continue over here. 11 9ths x squared equals 4. Tell you what, how about we multiply both sides by the reciprocal, multiply by 9/11ths, and we'd have x squared would equal 36 all over 11. So x would be two possible solutions, plus or minus 6 over root 11. Well, you already know what y could equal. So I could have x equaling 6 over root 11 positively. That means y would be x divided by 3, or 1/3 of that. So that would be 2 over radical 11. Z is just the opposite of that, so that would be z is equaling -2 over rad 11. So this you could call as your case 1. You could have, this is a potential absolute max or min. Well, in the same way, we could say, take a look at -6 over root 11. Then y is just x over 3, so that's -2 over root 11. Z would be opposite x over 3, so that's your 2 over root 11. So we're dealing with the following ordered triples. These are our critical numbers that are on the sphere, but we would expect them to be closest or farthest from that original point that we were given. And super fast, just helping you out, let's go back to the distance formula that we had originally. This distance formula up here can now be brought back down. And if we were to figure out what our distance was, and again, we could do this a couple of different ways. We could use technology to help us out. We could very quickly get the 89 out and say, well, my goodness, this distance formula that we had in there was the square root, and then we had parentheses, and what was it, x minus 3. Let me bring that up. Quantity squared, plus, then what, y minus 1, quantity squared, plus, and then we had z plus 1. And we'd have that quantity squared. And then we'll close our parentheses. So you can see that's more or less what we did. I think I forgot to type in x minus 3 over here. I think you can see I made a little bit of a typo. So I'm going to go fix that up. But now that I've closed that square root, I'm going to say bar, such that, then I'll say x equals, and what did we have? I think x was equal to what? 6 over radical 11. So I'll say 6 divided by the square root of 11. And then I need to say and, so I'll say catalog, and hit and y was equal to 2/11ths, or 2 over radical 11. Now hit and finally we'll have z equaled, what was it, -2 over radical 11. So we're almost done. And close the other parentheses. So you can see what's happening. We're just plugging that all in. Evidently we get radical 11 minus 2 when we work that out. So the distance was radical 11 minus 2. You might say, what if we were to switch the signs everywhere? Well, thank goodness we've already done the majority of that work. Let's real quickly fix that up. Change this to a -6 over radical 11. Change the y to a positive. No, I'm sorry. That's also a negative. So sorry, I'm going to have to type that in. And then change the z, I should say, to the positive. So we're almost there. So sorry, we're about to lose time. The other one's 11 plus